Breathe in, breathe out. We just exhaled a whole bunch of carbon dioxide. Carbon dioxide is an important gas for life on the planet. It is crucial to maintain the protective blanket around Earth, the atmosphere. Carbon dioxide is one of the primary greenhouse gases on Earth, which means that it helps the planet hold on to the heat from the sun so it doesn't all escape back out into space. If it weren't for this greenhouse effect, Earth's ocean would be frozen solid, and Earth would be a giant ice ball. It wouldn't be the beautiful blue and green planet of life that it is. Throughout Earth's history, whenever the amount of CO2 in the atmosphere has gone up, the temperature of the Earth has also gone up. And when the temperature rises, CO2 levels in the atmosphere increase even more because of the roles oceans play in the carbon cycle. As ocean temperatures rise, stored carbon dioxide from the oceans are released into the atmosphere, like a glass of soda losing its bubbles on a warm day. Carbon is something we need to keep tabs on now that emissions are becoming a super important component to track global warming and the planet's health. Around 45% of the carbon dioxide emitted by humans remains in the atmosphere, which is a key factor behind global warming. We need to be able to remove carbon from the atmosphere as well. That's where a technique called carbon sequestration comes in. It's also known as carbon capture, utilization, and storage. And it'll be vital to controlling our emissions. Removing carbon dioxide from the atmosphere and storing it is called carbon sequestration. The idea is to stabilize carbon in a solid or dissolved form so it doesn't escape into the atmosphere and aggravate global warming. This process has tremendous potential to reduce the collective carbon footprint from human activity. It can also prevent further emissions from contributing to our planet heating up. There are three main ways of sequestering carbon: biological, geological, and technological. Biological carbon sequestration is the storage of carbon dioxide in vegetation like grasslands and forests, or natural environments like soils and oceans. Forests. About 25% of the global carbon emissions are captured by landscapes rich in plants like forests and grasslands. When leaves and branches fall off plants or when plants die, the carbon stored in them is either released into the atmosphere or released into the soil. One challenge is that wildfires and human activities like deforestation reduce the power of forests as carbon sinks that capture carbon dioxide, and this is where grasslands come in. In some ways, grasslands and woodlands and wetlands are more reliable carbon sinks than forests because they don't get as easily hit by droughts and wildfires. Unlike trees, grasslands sequester most of their carbon underground. So even when they dry up or burn during wildfires, the carbon stays fixed in the roots and soil instead of in the leaves. Forests may have the ability to store more carbon in general, but in unstable conditions like we're seeing due to climate change, grasslands and wetlands are so much more resilient. Oceans. Carbon naturally goes both in and out of the oceans. These cycles can be thought of like an inhale and an exhale, where the net effect of these opposing actions decides whether more carbon is released or absorbed. Usually, the colder and nutrient-rich parts of the ocean can absorb more carbon dioxide than warmer parts. But warming oceans due to climate change mean that the holding capacity of carbon dioxide in the oceans is generally coming down. Still, oceans cannot be ignored, because they absorb roughly 25% of the carbon dioxide emitted from human activity. Soil. Carbon is also stored in soil. When plants carry out photosynthesis, carbon is stored as soil organic matter. It can also be stored in the form of inorganic compounds called carbonates. These carbonates have the ability to lock away carbon for more than 70,000 years, while soil organic matter typically store carbon for several decades at a time. Scientists are exploring ways to speed up this carbonate forming process by altering soil composition like adding finely crushed silicates that can store carbon for longer periods of time. If you don't go biological, you can always go geological. In geological carbon sequestration, carbon is stored underground in geologic formations or rocks. Typically, carbon dioxide is captured from an industrial source like steel plants, cement plants, or power plants and injected into porous rocks for long-term storage. There are physical and chemical ways of doing this. The physical mechanism, it involves trapping CO2 within a cavity of underground rock. These cavities are either large man-made ones like caverns and mines, or pore spaces in natural rock formations like depleted oil and gas reservoirs and groundwater aquifers. In the chemical mechanism of trapping CO2, carbon dioxide is transformed or chemically bound to another substance in the ground. For example, CO2 can be locked into a stable mineral form with calcium, as in calcium carbonate, or CO2 can be dissolved in underground water or reservoir oils. And now moving from the geological to the technological ways of capturing carbon, researchers are starting to look beyond simply removing carbon dioxide from the atmosphere and instead using it as a resource. Making graphene. Carbon dioxide can be used as a raw material to make graphene, which is used to create screens for smartphones and has a lot of other tech applications. While graphene production is done only by specific industries, it's a good example of how carbon dioxide can be used as a resource and as a solution to reduce emissions entering the atmosphere. Direct air capture. Carbon can be captured directly from the air using advanced technologies. In all honesty, this process is energy intensive and expensive. It could cost anywhere from 40 to 65,000 rupees per ton of carbon removed. While techniques like direct air capture are possible and effective, they are a bit too costly to implement on a mass scale for now. Engineered molecules. Scientists are also experimenting with molecules that can single out and capture carbon dioxide from the atmosphere. These engineered molecules act as a filter, only attracting the element it was meant to seek out. That's all well and good, but who's actually doing carbon capture in India? Carbon sequestration is a cumbersome and expensive process. So at this stage, there are no large-scale carbon capture and storage projects up and running in India. Most of the carbon capture underway is being done using the biological route, using afforestation. And this isn't meeting the targets we've set for ourselves as a country. India has taken a target of channeling an additional 2 billion tons of carbon sequestration by 2030. It's not clear exactly what mix of biological, geological, and technological methods will be used for this, but it's a target nonetheless. There are plans in place and companies working on the tech to get us there. The government has also set up 2 centers of excellence specifically for carbon capture, utilization, and storage. One is the National Center of Excellence in Carbon Capture and Utilization at IIT Bombay. This center will be involved in defining milestones, spearheading the science and technology innovation in Indian industry, and accelerating R&D in the carbon capture and utilization sector. The second is the National Center in Carbon Capture and Utilization at the Jawaharlal Nehru Center for Advanced Scientific Research. This center will work on developing the materials and methods that can be scaled up to produce useful chemicals and fuels from carbon capture and storage projects. It will also promote carbon capture and utilization research, provide training, consultancy, and bring out solutions that have an economic and social impact. As for the private sector in India, carbon capture technology facilities are being set up at the National Aluminium Company Limited, Oil and Natural Gas Corporation, Bharat Heavy Electricals Limited, Andhra Pradesh Power Generation Corporation Limited, Reliance Industries Limited, Unilever, and Dalmia Bharat. There are also startups like Bhumitra and Varaha that are working in the carbon capture space. Evidently, we have a long road ahead to get carbon capture in India to where it should be. It's all up to technology and innovation to bring the cost down and make carbon capture technology more available to industries and eventually individuals. It's going to be an interesting journey to see how India's carbon capture protocols shape up in the run-up to 2030. In the meanwhile, we'll have a podcast or two about how significant this technology really is in the climate tech space in India. There's a lot more from the world of climate technology coming your way on Biotic. Thank you for watching. See you in the next one.